Mr. Poe from Wilmington Grammar School for Boys, and today in the 9th session for Geometry and Vectors I wanted to look at conic sections. Now you could probably argue, well, you know, isn't this a little bit of differentiation, a little bit of other things going on? But I'm going to put it in terms of coordinate geometry. I'm going to be looking at some special cases. So some of you up to GCSE should be familiar with the whole y equals x squared u-shaped parabolas. Okay, so if I was to draw it, it would kind of look like this. And we should be familiar that these things are called parabolas. Today we're going to be looking at conic sections, and they're a family of curves. And what I want you to do is imagine a cone, an upside down cone like this, and at that point there we're in three-dimensional coordinate space. So there's the x-axis, there's the y-axis, and the z-axis is going right through the middle of this cone. Okay, and what I want you to imagine is that there's an inverted cone underneath it as well, and it goes on forever. I've only drawn it as a finite object because I'm running out of space, but imagine we've got a cone. That is terrible. And it's such that something like that maybe. And it's constructed in such a way that this is a straight line and this is a straight line. It's just the exact same cone but flipped upside down, stuck point to point. Okay. Now what we need to imagine is pretend I will take a plane and I slice off. So it's going to go through there and there, say. I slice off a part of the cone. Well, what would that look like? You can try this for yourself. If you had a cone and you took a slice like that, you would create a U-shaped parabola, and there would be a flat surface face looking like this on where the cone would be. Okay, I know this takes a lot of mental imagination, but if you've got a cone and you take a slice, well, actually, let's get this more realistic. Let's get these running parallel for a start. Oh dear, that's looking like that. Say I've got something like that going on. I take a slice through my cone like so. Well, you'd get a parabola. Okay. Now, what I'm also claiming is that if you was to take a horizontal slice, like so, then this would trace out an ellipse, a circle. Okay, let's make this a bit bigger, this will be here all day. That would trace out a circle. And the point is, what we're going to be doing today is angling these cuts so they form different shapes. So, oh dear, oh, didn't want to do that. Oh, I'm such a silly boy. So, if it's perfectly horizontal, it will make a circle or an ellipse, and depending on the angle, oh mate, come on. So we should all know what a circle looks like. It's a circle, it's looking like that, centre at the origin. Then this is going to be, that's X, that's Y. This is a circle or an ellipse. And ellipses you can think of as like the ovals, and circles are the special case when it's completely symmetrical, rotationally symmetrical. So think of circles as special cases of ellipses. In actual fact, you're not going to be able to see that particularly well. So let's turn this to like a darker green. Let's turn these things to a darker green. There you go. And then you're probably thinking, okay, so what if I take this at a completely vertical angle? So let's say now I'm orange and I draw a line like so, like that, and I can take a completely vertical slice like so. Then what kind of shape do you think is going to happen? Well, it's going to be there and there, and it's going to make some kind of U-shapey type thing, and it's going to be here and back here, and it's going to make an N-shapey type thing like that. And technically this would be the side that'd be left off, and this would be the side that's left off. And what we call this shape, actually, so it would be more like this. You'd have something like this, maybe. This. Okay, now these are a little bit more difficult to work with. These are called hyperbole. Some people say hyperbola. I just say hyperbola. The plural is hyperbole with an E on the end. You don't say hyperbolas, it's just hyperbole. Plural of parabola is parabole, not parabolas. Although you can say parabola. To be fair, no one's going to particularly argue with you. You know what they mean. So there's quite a lot to get through here. If you're wondering where these equations come from, then I'll give you a hint, and you can work through this yourself. The equation of this infinite cone top to tail is z squared equals x squared plus y squared. So that's the equation of the cone, of this upside down cone, or rather the top and bottom cone. And you should know the equation of a plane, and you can probably tell straight away that the green one is just when z equals some constant. And so when we've got the circle, we're just going to have x squared plus y squared equals z squared, but z is some constant, so that'll just be some r squared. So when that k is r squared, then the radius of this circle is just r. That's probably the easiest one to prove. If you want to go away and prove that these shapes actually do cause, you know, these intersections of the cone and the planes do cause what they do, you have enough tools now, actually. So I'm quite happy for you to go away and figure this out. However, what I want to be looking at today is some of the properties of these things. So, for a start, a couple of things I wanted to talk about. One, when it comes to a parabola, well, in actual fact, when it comes to all of them, oh dear, pardon me, I want to define these conic sections in a slightly different way. And I want to talk about something called eccentricity, or eccentricity. Okay, and to get this under your belt, then I need to talk about a few things. One, I need to talk about a focus, and I need to talk about a directrix. I cannot spell to save my life. A directrix. Okay. So what do I mean a focus, and what do I mean by a directrix? So let's imagine I'm on the XY plane. There's my x-axis, there's my y-axis, there you go. Now, let's say a focus is a particular singular point. Let's say the focus is here. Let's call it F. Okay, now the directrix, this is a line. Okay, so imagine a horizontal line like so, where this is my directrix D. Okay, now let's suppose that E is the ratio of the distance from the focus over the distance from the directrix. Okay, so I think that's the right way around. We'll soon find out. Because okay, so imagine, right, these things are equally spaced. So I don't know, let's say for argument's sake that this point up here was at the point, let's say some A, so this is 0A, and where the directrix meets the y-axis down here, this is 0 minus A. So they're symmetrical across the x-axis. Then what were to happen if E equals to 1, i.e. the distances are the same? Well, if I was to draw in purple, the first easiest point you'd know is the origin, 0, 0, because clearly this distance is the same as this one. If E was 1, then you have a fraction where the top equals to the bottom. Now you're probably thinking, okay, so what other points satisfy this? Well, let's pick another point, let's say over here. Then in order for E to be 1, we need the distance from the focus, which is from here to here, to be the same as the distance from that point to the directrix, which is there to there. Now, according to this, according to this diagram, it looks like the distance from the directrix is a bit too big, so maybe we need to lower this maybe. Spoiler alert, it's going to look like this. So in E equals to 1, we have a parabola. Okay, and now there's a couple of useful things to take away from that. One of them is, how do I know for any parabola where the focus is? Well, the focus is always going to be, when it's in the form y equals, well, let's get the way round. When x squared equals 4ay, in this case, then a, 0, is the focus. So, say for example, I'm dealing with y equals x squared. This is in the form of 4 lots of a quarter y equals x squared. And so this number is a quarter, so that means I'd have a focus at 0 quarter, I'd have a directrix at 0 minus a quarter, and it's what you'd expect it to be. Okay. Being able to write constructions as a loci of points is incredibly useful. So when we've got a directrix, that is just going to have equation y equals negative a. And now we can actually pull a similar trick to this, because there's other parabolas you can have. They can be all kinds of rotations. But another key one you might see is if y squared equals 4ax. And what would that look like? Well, it'd be exactly the same thing, but this time the focus is A on the x-axis. The directrix is at minus A on the x-axis, and it will be like a C-shaped parabola. It would be the same kind of shape but turned on its side. And same deal, the focus will just be... Whoa, I've got this the wrong way around, haven't I? This should be 0A. The focus over here will just be A, 0, and the directrix will be x. Will just be x equals to negative A. Okay, so when the eccentricity, the ratio between the distance from the focus to the graph and the distance from the directrix to the graph equals 1, then we've got a parabola. And generally speaking, there's two main forms for which the equation of a parabola comes about. And it's usually when x squared equals to some y, or some y squared equals to some x. There may be some translations or something like that, but in general, that's pretty much it. Now, I might want to add some more pages. Now, what happens, so this was in the case of a parabola, so I can shunt all this down. So this is the case of a parabola. And really, this should have been up here. Okay, so what about... by the way, parabolas, be careful for parameterizations. So example, another way of writing a parabola would be, say, x equals 80 squared and y equals 280. You know, there's various different ways. The point is, these functions, sometimes x might be a function of t, sometimes y might be a function of t, and generally speaking, you'd have to use your wits about you to work out what these functions are, or they might just give it to you in the question. It's not that particularly difficult. If we then look over to the next easiest one, which is ellipses, and this is a little bit more tricky, but the general ellipse, okay, and you can move these around by translations or reflections or anything like that, is, well, this case, actually, the ellipse is a bit special because there's two foci. And one of them will be here, and one of them will be over here. And for the general equation for an ellipse, we're looking at x squared over some a squared plus y squared over b squared equals to 1. And the eccentricity is between 1 and 0. Okay. Now, there's also directrices, and they're on the outside like this. Like here and here. And the equation the ellipse would trace out would be something like this. And now let's write a few points of intersection. Well, it would intersect the y-axis at plus or minus b. It would intersect the x-axis at plus or minus a. The foci would be positive AE0 or negative AE0. And the directrices would be x equals a divided by e and x equals minus a divided by e. Okay, really important. Now, there is a way, so what I'm actually saying is the distance from here to here is shorter than the distance from here to here for that focus, and the distance from here to that same point is less than the distance from there to there, so that's corresponding directrix. Okay, so this pink distance is shorter than this pink distance, and this corresponding green distance is shorter than this corresponding green distance. That's what it means to have an eccentricity of between 0 and 1. i.e., all of those points are nearer their respective foci than they are the directrices. Okay, and if you want the ratio of all those points, it will be whatever E is. Now, there is a very special link. Now that I know what the foci are, you can actually probably work it out for yourself, but you're given this in the formula sheet that b squared equals a squared times 1 minus e squared. Now this is quite important because sometimes they won't actually give you the eccentricity of the ellipse. You'll have to work it out. And luckily for you, this is in the formula booklet, so you don't have to worry about it. But if you do it a couple of million times, you'll kind of memorize it anyway. And where it comes from is you can just pick a general point, and you can do Pythagoras to work out this distance, and then work out this distance, and so on and so on and so on. And it's a really nice result. By the way, it should be obvious, actually, that the distance, this distance, and this distance is always going to be constant wherever you are on the ellipse, because as I trace that around, that distance is just going to be the total distance between the two directrices. However, what is a more surprising result is as you go around the ellipse, that the distance from that foci plus the distance of that foci is always a constant as well. Okay, and you know, another way of checking to see if you do actually get an oval or an ellipse is imagine you've got a safety pin there, a safety pin there, and you've got some string that goes around it. It's a bit slack, say. You put a pen in the middle, and then you pull the pen out taut, and then you try and trace out the biggest shape that you can, and you will actually get an ellipse. Now you're probably thinking, hold on a minute, where do circles come into this? I don't understand. Well, think about it. Circles are essentially when you move these foci inwards and inwards and inwards until the very special case when both foci are on the origin. Okay, and when both foci are on the origin, you've essentially got a circle, haven't you? Now I'll leave that for you to prove, but I'm hoping it should just make intuitive sense at this point. Now, how do I know that the intersections are A, B, and minus B? Well, that's pretty easy. If I make y equals to 0, then I've got x squared over a squared equals 1, so x equals plus or minus the root of a squared, which is plus or minus a. And then I could do the similar thing. I could substitute x is 0 in to work out what the y coordinates are. That's not that big of a deal. And again, you'll see loads of parameterizations with this, so just be really, really careful. Okay, now, and by the way, you know, be also aware that if you've got funny things like, say, x minus 3 all squared, then this is just everything moved right 3. Yeah, and if it was y minus 3, then that means everything has been moved up 3. Okay, we no longer have y as a function of x here, so that rule of inside the brackets not as expected thing applies for all variables. So it's always not as expected when it's not an explicit function, y a function of x. But to be honest, you can just substitute values in and just figure them out for yourself. It's honestly not that bad. The last thing I wanted to talk about was the final thing, was the hyperbole. Okay, and if you hadn't guessed, We've looked at the case when e equals 1. We've looked at the case when e is greater than 0 but less than 1. So we're now going to consider the case when e is greater than 1. Now e can't be negative because you can't have the ratio of distances being negative, because distances are positive quantities, so that just doesn't make sense. Now I've left it to last because there's various things the hyperbola could actually be. I'm going to probably take the most general one, and that's when x squared over a squared minus y squared over b squared this time equals to 1. But I'll also consider the case where y squared over b squared minus x squared over a squared, not b, equals to 1 as well. Okay, so let's think about what's going on here. Well, when y is 0, this term disappears and I'm left with x squared over a squared equals to 1. So I know that x definitely goes through positive a and negative a. I also know that when I get rid of x, I set that equals to 0, I'm going to have minus y squared equals to b squared, and that has no solutions because a negative number can't equal a positive number. So I know it's never going to cross the x and y axis. Next up, if I add y squared minus b squared to both sides and minus 1, I get y squared over b squared equals 1, I get x squared over a squared minus 1. And if I times by b squared both sides, then I get y squared equals b squared over a squared x squared minus the b squared. Now look what happens. As x tends to infinity, then this term is going to dominate. So the b squared doesn't particularly matter anymore, and it looks like y is going to tend to infinity as well. Or technically, y could have been negative infinity as well. Either way, when x and y is particularly large, that b squared cancels, and this can be approximately, y can be approximately equal to plus or minus b over ax. So it's never actually going to be that because I've got a minus b squared term here, but I've actually got two asymptotes looking like this. Not necessarily 90 degrees perpendicular, where one of them is y equals positive b over a, and the other is y equals negative b over ax. And then I know that when x tends to infinity, y tends to infinity, and it approximates that. And if I know 2 points already, I know that this curve is going to do something like that and something like that. I've drawn that terribly. So let's say it's doing something like that. And then by symmetry, this is going to be going over there. So I've got these two C-shaped things. And that should make sense because these two shapes are these orange shapes up here that I was thinking about. So I am looking for this hyperbola thing looking like that, albeit that it's rotated 90 degrees. So, but it's still a thing. Okay, let's now, by similar logic, consider what's going on here. And it's pretty much going to be the same thing, isn't it? The only difference is the x and y's have switched over. So I'm still going to have, it's going to cross the y-axis at a and minus a. But this time, I'm still going to have asymptotes, diagonal asymptotes like this, and this is going to be y equals positive b over ax, and this is going to be y equals minus b over ax, and it's going to look like that. Okay, right, cool. Now let's put some facts on there that you're going to need. Right, for a hyperbola, it's the same deal, but this time, because e is greater than 1, it's now b squared equals a squared e squared minus 1. Notice how the 1 and the e squared have now swapped positions. It's not 1 minus e squared anymore, it's e squared minus 1. And that has to be the case because now e is greater than 1, so 1 minus e squared is going to be a negative quantity, and you can't have that being positive. You can't have that being negative, sorry. Okay. Next up, let's have a look at the foci and directrices of these things. Well, for hyperbole, the foci is actually, in this case, x equals plus or minus AE. So let's think about what those things are. Since E is bigger than 1, that means the focus is going to be over here, which is bigger than A, and it's going to be to the left minus AE, like that. The directrix here, in this case, is going to be x equals plus or minus A over E. Okay, so since E is bigger than 1, then what we've got actually is a directrix that's to the left. So this is x equals A over E, and this directrix here is x equals minus A over E. And what we're going to have is the distance from any point, from here to here, say from there to say here, like that. We're now actually wanting that this side is a bigger distance and this is smaller. I haven't drawn it particularly well, but it should be. In actual fact, I could have moved that orange bar to the right a little bit, so it's a little bit nearer maybe. Let's do that. So let's say the directrix is now here, where it crosses AE on the x-axis, and now for a hyperbole, the perpendicular distance between that point is now a lot smaller than the distance from the foci to that thing. Yeah. Now, proving this isn't that big of a deal. It just takes time, and I'm feeling confident that I've given you. Well, let's look at the foci in this case. You can probably deduce actually it's just going to be y equals plus or minus AE, and the directrix is just going to be well, no, the foci are points, aren't they? So this is actually going to be 0, comma, plus or minus AE, and over here this is going to be plus or minus AE, comma, 0, and the directrix is just y equals plus or minus AE. Okay. Now, proving these things isn't actually that big of a deal. I will say, however, that when we parameterize hyperbolics, we tend to use hyperbolas. Sorry, oh Lord, I've given the game away. When we parameterize hyperbolas, we tend to use hyperbolic functions. So sine of some t maybe, cosh of some t, and so on and so on. Now, when we parameterize ellipses, we might have, say, x equals, let's say, a cosine t, and y equals b sine of t. And then if you think about it, what does that mean? Well, that means x over a equals cosine of t, and y over b equals sine of t. And then clearly if I square both sides, I will be left with x over a all squared plus y over b all squared equals to 1. Because sine squared plus cos squared equals to 1. And then with hyperbolics, I can pull a similar trick. I can let x equals a cosh t and y equals to b sine t in this case. and then I can say, well, x over a equals cosh, hyperbolic cosine of t, and y over b equals hyperbolic sine of t, and then I know that cosh squared t minus sine squared t equals to 1. So I'm going to have x squared over a squared minus y squared over b squared equals to 1. Or I could swap these two things around. I could make x equals to a sine t and y equals to b cosh t. And the point is the formulae would just come out and about of it. You know, I've given you all the breadcrumbs of how to follow this. If you want to, just plow on and get on with it. To be honest, I just want to get on with some practical examples. I have been thinking, actually, now that we're getting on to harder stuff, I do want to talk more, don't get me wrong, but I kind of feel I want to make my videos between an hour and an hour and a half. It's only really special cases of like step videos and stuff I want to go on for 2 hours. One, it's just practically, it's tiring. Yeah, that's mainly it. Okay, so let's just crack on with some questions. So if you feel like you've got everything and you've made some notes, have a go at this and pause the video. Okay, a hyperbola h has equation x squared over a squared minus y squared over 25 equals 1. The foci of h at the coordinates 13, 0 and minus 13, 0. Find the value of a. Okay, so first of all, I'll look at the hyperbole and I'll know that the foci is plus or minus AE 0. So I know that 13 equals AE. Okay, next up, I also know that for hyperbole, that b squared equals a squared lots of e squared minus 1. Okay, well, I know what b squared is because b is 25. B squared is 25. Remember, this is in the form x squared over a squared minus y squared over b squared equals to 1. So I know that 25 equals a squared times e squared minus 1. Okay, well, to work out the constant a, I can just solve simultaneously these two equations. So I can make e equal to 13 over a. So this equation becomes 25 equals a squared lots of e squared, which is 169 over a squared minus 1. If I times this all out, I'll get 25 equals this times this cancels, get 169, and this becomes minus a squared. So if I add a squared to both sides of minus 25, I get 144. So a appears to be 12 plus or minus 12. But it says a is a positive constant, so therefore I can deduce that a is 12. So that wasn't too bad. That was just using the information we'd seen and learnt so far and just solving simultaneously. B, find the equation of the directrices of h. Well, the directrices are x equals plus or minus a over e, are they not, from the hyperbole? Yep, they are, in that case. Well, I know what a is, I just need to work out what e is. Well, if a equals 12, then 13 equals 12 times e. So e equals 13 over 12. So that means the directrices are plus or minus a, which is 12, over e, which is 13 over 12. So I believe that's plus or minus 144 over 13. So the two directrices have components x equals plus or minus 144 over 13. So that wasn't actually too bad. That was a nice warm-up question, just testing your knowledge, what you've seen so far. Actually, that was quite easy. Okay, let's try something harder, hopefully. Pause the video if you want to give yourself a little go. This looks more difficult, but let's try it. Okay. The hyperbola h has equation this, where a and b are constants. The line L has equation y equals mx plus c. Given that L and h meet, show the x-coordinates at the point of intersection are the roots of the equation, blah. Okay, well, if I want to solve simultaneously, I just need to replace the y with mx plus c. And then that's something for x to solve. So I actually want to solve x squared over a squared minus mx plus c all squared over b squared equals to 1. Okay, well, I think I just need to... What does this say? It's got x squared, lots of stuff, and then it's got x, lots of stuff, and then constants. So really, there's not a lot to do here other than just expand. So if I times everything by a squared, b squared, this becomes a squared, b squared, and this becomes b squared, x squared, and this is minus a squared, lots of mx plus c, all squared. So let's just deal with it. So I've got b squared x squared minus a squared lots of, and if I expand this double brackets, I'll have m squared x squared plus 2mxc plus c squared, and this equals a squared b squared. If I collect up the x squared terms, I'm going to have a b squared minus a squared m squared, so that's b squared minus a squared m squared. Plus the x terms, and I think the only x term that's going to pop out of here is the minus a squared times 2mxc, so it's going to be minus a squared m times 2c. And then the constant term is just going to be minus a squared c squared, so it's minus a squared c squared, and this equals to a squared b squared, like so. Well, if I bring everything over to the other side, to set this equal to 0, then the amount of x squareds gets multiplied by minus 1, so I've got x squared lots of a squared m squared minus b squared. I've actually got the positive of this thing, so plus x lots of 2acm, a squared m, and then I've got plus a squared lots of b squared plus c squared. So unless I've made a horrendous mistake, I think that's it. So let's double check. I've got a squared, okay, so I've got a squared m squared minus b squared lots of x squareds, that's check. I've got 2a squared cm, so I've got 2a squared mc. I don't know why they've done it not alphabetical. And then a squared lots of b squared plus c squared. And again, why would you put c squared plus b squared? Why don't you just put it alphabetical? It doesn't matter. The point is I've gotten what they want me to do, so that's fine. So that's a done thing. Hence, given that L is a tangent to H, interesting, show that a squared m squared equals b squared plus c squared. Okay, so this is part A. Part B, how do we know what a tangent to hyperbola would be? Okay, well I'm definitely going to need more paper for this, so that can shush. Okay, so let's double check. I've got x squared over a squared minus y squared over b squared equals to 1. Is that true? Yep. And essentially I want to find dy by dx of this thing. Do I? Okay, yeah, let's go for it. So the gradient of this thing, because it says L is a tangent, so m must equal the tangent of this thing. So, okay, so if I make, well, I could just differentiate. So x squared over a squared will differentiate to 2x over a squared, minus y squared over b squared by implicit differentiation becomes 2y over b squared times dy by dx, and 1 differentiates to nothing. If I add this term over, essentially I've got 2x over a squared equals to that. I can divide by 2 to get this. I can times by b squared and divide by y to get dy by dx equals to this. And I'm saying that our m is this value. Okay, for our specific thing. Okay, so I've now got to rearrange m equals b squared x squared over a squared y squared. Not y squared, just y. Well, that's nice because I've got a squared, m squareds, b and c's here. But I've only got... this is not an x squared, is it? That's an x, you silly boy. Well, I know what m is. That's mx plus c, isn't it? I know what y is. Y is mx plus c for that to be true. So if I rearrange this, I'm going to have m, lots of a squared, lots of mx plus c, and this equals b squared x. If I expand this, I'm going to have a squared m squared x plus a squared mc equals to b squared x. And I want a squared m squared the subject. Right, how's that going to work? L is a tangent to h. Yeah, I've got that. dy by dx is definitely that. It's 2x a squared. Okay. Well, where is the c squared going to come from in this? I don't think this is the way forward. Okay. How does this work? Oh, God. Oh, wow. So, if it's a tangent to h, there's only one solution to this thing down there. Oh, God. Yeah, okay. I'm massively overcomplicating this. If there's only one solution to this thing, then that means the discriminant is b squared minus 4ac. That equals to 0. It's got one repeated solution. So that's 2a squared cm all squared minus 4 lots of a, which is a squared m squared minus b squared, times by c, which is a squared b squared plus c squared. That equals to 0. Well, if that equals to 0, then I can just set one side equal to the other. On the left hand side, I'm going to have 4 lots of a to the 4 c squared m squared. And then that 4 can cancel with this 4. Then I'm going to have this term times this first term, so it's going to be a to the 4 m squared b squared. And then I have that term times by the next two terms, so I'm going to have plus a to the 4 m squared c squared. And then I'm going to have this term times by these two, so it's going to be minus a squared b to the 4. And then this times by these, so it's going to be minus a squared b squared c squared. Wow, that's not particularly helpful at all. Well, they've all got a squared as a factor, haven't they? So I could take a squared out. So this is a squared m squared b squared plus a squared m squared c squared minus b to the 4. Really? Wait, how is that minus b to the... Yeah, no, it was minus b to the 4. And then minus b squared c squared. So this is going to equal a to the 4. No, yep, still. A squared c squared m squared all times by a squared. So that can go, that can go. And what am I aiming for again? A squared m squared. So really I'm going to have to divide by c squared, aren't I? So I've got a squared m squared on that side and divide everything by c squared. I'm going to have a squared m squared b squared over c squared plus a squared m squared minus b to the 4 over c squared Wow. Minus b squared. Oh, really? How is this a thing? How's this gonna work? Wait a minute, I feel... Okay. What could I do here? How does this help? How does this prove that that's the case? I feel like... How does this work? Wait a minute, I think I'm just getting mad confused here, because I've got a this on that side and a this over there. So when I just subtract them, oh man, I'm just being silly. I'm going to get 0 equals a squared m squared b squared minus b to the 4 minus b squared c squared. If I divide by b squared, that drops down to a squared, and that becomes a c squared. And then yeah, this falls quite nicely. A squared m squared equals b squared plus c squared. And this is all assuming, well, I've done lots of division here, that a, b and c do not equal to 0. Well, they can't do. It would just be dumb otherwise. Okay, the hyperbola h dashed is that, so it's a specific case of this, find the equations of the tangents to h bar which pass through the points 1, 4. Okay, well, I think I can just bang this out straight away now, because I now know that a equals to 5, b equals to 4. I don't know what c is, and I don't know what m is. But if I know that y equals 4, m lots of 1 plus c, so I know that m plus c equals 4. I know that a squared, which is 25, lots of m squared, equals b squared, which is 16, plus c squared, which is 4 minus m all squared. Now I can deal with this, right? So I've got 25m squared equals 16 plus 4 squared is 16 minus 8m plus m squared. I can minus m squared over, so that's 24m squared. I can plus the 8m, so that's over there. And then I can minus the 32 to make that equal to a 0. I can believe I can divide all of this by 8 to get 3m squared plus m minus 4 equals to 0. So I'm actually going to get 3m, Is this a thing? No, other way round. So that should have been a +4, that should be a -1. Yeah, that factorizes. So either m equals -4/3 or m equals to 1. In which case y equals 1x and m plus c is 4, so that must be +3. And the other one is y equals -4/3 x. And then -4/3 plus what equals 12/3, which is 4. Well, that's got to be 16/3, isn't it? So actually, that was surprisingly easy. So I guess by doing this long-winded thing, we've actually managed to get the two equations of the tangents passing through 1, 4. Working quite nicely. Yeah, done. Coolsies. And this is the last one. Cool. So hopefully this is going to be a fairly short video today. Okay, so the hyperbola, or pause the video, give it a go yourself. The hyperbola h has equation this. Use calculus to show the equation the tangent to h at the point a cos theta b sine theta may be written in the form of this. Okay, so I'm just going to differentiate that. So differentiating the equation, that is going to become 2x over a squared minus 2y over b squared times by dy by dx equals to 0 by implicit differentiation. So dy by dx is going to equal, well, the 2's cancel, so it's going to be x over y, and this is b squared over a squared. Now we're told that x equals a cos theta and y equals b sine theta. So the gradient at a general point is actually going to be b squared times by x, which is a cos of theta, all over a squared times by y, which is b sine of theta. So what's going to happen is that a is going to cancel with one of these a's, that b is going to cancel with one of these b's. So the gradient in general is b cos of theta over a sine of theta. And I want the equation of the tangent, so all I know is a gradient and it goes through a point, which is there. So I could just jump straight into it, and that's y minus the y coordinate, which is b sine of theta, equals the gradient, which is b cos of theta over a sine of theta times by x minus the x coordinate, which is a cos of theta. And I want this to equal AB. Right, so let's tidy this up. I've got y minus, well, if we times everything by a sine theta, then I've technically got y times a times sine theta minus ab sine squared theta equals x times b cos theta minus ab cos squared theta. And then what I'm going to do is I'm going to add this cos squared ab to that side. And remember that cos squared theta minus sine squared theta equals to 1 because of Osborne's rule. So if I times this by AB, that's just going to equal 1 times AB. So actually I'm going to have AY sine of theta, and then that's going to be plus AB equals to BX lots of cos theta. And what, I want this equal to AB, do I? Yeah, so I'll just minus the AY to the other side. So BX cos of theta minus AY sine of theta is going to equal AB. So BX cos minus AY sine is there, and this equals to AB, so tick, that's done. Okay, that wasn't too bad. Part B, the line L1 is a tangent to H at the point this. Right, given the tangent, given that L1 meets the x-axis. Okay, so L1 is just satisfying this thing up there. Okay, fine, that was a bit weirdly worded. Given that L1 meets the x-axis at the point P, find in terms of A and theta the coordinates of P. Well, if it meets the x-axis, then y is 0. So at P, we have AB equals bx cosh of theta minus A times by 0. Well, just y is 0, so it's just this. So if I divide by B and then divide by cosh theta, I've got x equals A over cosh of theta, which is the same as A of sech theta. I believe that's all they wanted it to. Yeah, give it in terms of A and theta, done. So the coordinates of P are technically A sech theta, comma 0. So that's P. That's my answer for part B. Okay, part C. The line L2 is a tangent to H at the point A0. Right, so I'm going to replace X and Y with A. Okay, so this is the line L2 and it goes through the point A0. Hold on, L2 is the tangent to H at the point A0. Ooh. Okay. Given that L1 and L2 meet the point Q. Okay. So what is the equation of L2? Well, it would be AB equals BX. Well, that would be B times A, which is AB, cosh of theta, minus, and then Y is 0. Well, lol, that's, well, obviously that's just when cosh of theta equals to 1. So that's a bit weird. Find in terms of, okay, so what is the equation of L1 is a tangent okay. So the information I get from L2 is that cosh of theta equals to 1. And if you remember what the cosh diagram looks like this, when it's 1 when theta equals to 0, so that means sine of theta equals to 0 as well. So find in terms of A and B the coordinates of Q. I believe that's just when cosh is 1 and sine theta 0. Okay. Have I done this right? If it goes to the point A0. L2 is the tangent to H. Point A0. I feel like I'm missing something here. That hyperbola is that. What does this hyperbola look like again? So it's going to cross at A. Oh God. So if L2 is the tangent to H at the point A0, it's just going to be the line x equals A, isn't it? It's just going to be that vertical line x equals to A. Fine, so when does x equals to A? And now I need to substitute it into here because that's the line of L1. Right, okay. So we have got to solve AB equals to AB cos theta minus AY sine of theta. If I divide everything by A, that A goes, that A goes, that A goes. If I make Y the subject, then Y equals, and then I have B lots of cos theta minus 1, because I've minus that B over, and then I've divided that all by sine of theta. And then I already know that it's on the x equals A line, so the coordinates of Q is just A lots of B cos of theta minus 1 over sine of theta. Wow. I almost forgot to draw a sketch. It's always good to draw a sketch. So what's happening is over here, the whole hyperbola is h. Let's say this is the point P, so the tangent to that P is looking like this. Over here, this is the line L2, this is the line L1, and they meet at this point here, which is Q. Let's get rid of the... Don't need the asymptotes, we know what the asymptotes are. Okay. Show that as theta varies, the locus of the midpoint of PQ has equation this. Okay, so I need to find the midpoint of P and Q. So what is... Okay, so where was P? P was this and Q was this. So the midpoint of the two is when you add the two together, which is A lots of sec theta plus 1 all over 2. Is that right? Yeah. And then the coordinate is going to be B cos of theta minus 1 over 2 sine theta. That's definitely going to be the... Yeah, that's fine. Oh wow, so now we're going to have to link the two together. So if this is the new x coordinate and this is the new y coordinate, then how are x and y related and show that it satisfies this? Oh wow. Wow, wow. So let's write this down. What is x 4y squared plus b squared equals to ab squared? Okay. Let's see. Okay, so I've got to show that these two things satisfy that. Right. Oh boy, this is not nice. Well, first of all, let's get rid of this sec stuff. So this is A lots of 1 over cos theta plus 1 all over 2. And if I times top and bottom by cos, that becomes a 1. This becomes a cos, and this becomes a cos theta. And now we have B cos theta minus 1 over 2 sine of theta. Okay. Well, let's work out what we're supposed to prove. We're supposed to prove this thing is the case. So what is... We've got to prove that this thing squared times by 4 and then add b squared, if we then times it by x, which is this thing, equals to ab squared. That's essentially what we're trying to do. If we can show this, then we're okay. Oh man, that's not cool. That is not cool. Anyway, let's do some things. Well, first of all, the 2 and that 4 will cancel. On the top, I'm going to have b squared lots of cos squared theta minus 2b squared cos theta plus b squared. And then I'm also going to add a b squared sine of theta, so that this can all be over a common denominator. Sine squared of theta, so this can all be over a sine squared theta. Yes. Let's see. Cos squared minus 2 cos theta plus 1. Yep. Cool. And now this will become this will be an a plus a cos theta all over a 2 cos theta. Oh man, this is not cool. This is not cool. Right. Okay. Well, first of all, let's take the factor of a out. So that's a, so that's 1, and that's cos theta. Next up, let's take the factor of b squared out. So that b squared can go, b squared can go, b squared can go, b squared can go. That's a 1, and a b squared's here. So I've got to somehow show that these two things are pretty much the same. Okay. I'm getting confused here. So minus 2. Yeah, no, that's fine. I shouldn't put a massive gap there. That's confusing. Right. So let's deal with this then. So let's turn this sine squared into a cos squared. So cos squared theta minus sine squared theta equals to 1. So that means cos squared theta minus 1 equals to sine squared. So this whole thing on the right hand side becomes cos squared of theta minus 2 cos theta plus 1 plus sine squared, which is cos squared theta minus 1. And this is all over sine squared theta. Okay, this is a thought bubble. I don't need this. Whack it over here, make it small. This is still 1 plus cos of theta all over 2 cos of theta. Right, are there things we can do here? Well, the 1's cancel, and I've got a 2 cos squared theta there, so that can go. And then this 2 can cancel with these 2's when I factor it out, and that's not a problem. Okay, so what's going to happen is I'm going to have 1 plus cos theta here, and then these two things factorise to cos theta times by cos theta minus 1. This all becomes over cos theta times by sine squared theta. The cos thetas cancel. This is a difference of squares, and this is actually cos squared theta minus 1, which we all know is sine squared of theta. So these two cancel with this, and this equals to 1. So we are left, in fact, with ab squared equals to ab squared. So that is actually done. Cool. Cool, that was meaty. So yeah, difficult stuff. A lot of it is just how good your algebra differentiation is. But work through the problems, familiarise yourselves with them. The key thing is to get, what the eccentricity facts are, what E is in terms of A and B, what the Foci and directrices are. And yeah, hopefully you enjoyed that. Toodaloo.